Welcome to RR Max channel. I am starting reduction formula this time because I have been using this integral sine to the power of x nx dx formula in the definite integral. So I thought I would just revise all the formulas that appear in the reduction formula. The first one is evaluating integral sine to the power of nx dx. I call this integral as n. The suffix n and this power are related, and that will be used in the reduction formula. To derive this formula, I am going to use integration by parts, where it is u is taken to be sine to the power of n minus 1 into x, and the dv is taken to be sine x dx. So that du is n minus 1 into sine to the power of n minus 2x into differential of sine x, which is cos x, and v, when you integrate dv, you will get minus cos x. I'm using integration by parts formula, which states uv minus integral v du. So u is sine to the power of n minus 1 into x into minus cos x minus integral of v du. So that's minus cos x into n minus 1 into sine to the power of n minus 2x cos x dx. Now this, there is no limits here, so currently we will retain them as it is, and always this n for us will be positive integers. So sine to the power of n minus 1 into x into cos x, I'm taking out n minus 1. This negative and negative sign makes it positive, and now this reduces to sine to the power of n minus 2 into x into cos square x. In the next step, I will replace this cos square x as 1 minus sine square x, and this you multiply and will take it as two different integrals. So that gives you minus sine to the power of n minus 1x cos x plus n minus 1. First integral will be integral of sine to the power of n minus 2 into x dx, which is replaced as I suffix n minus 2. And then next you have a negative sign, so it's minus n minus 1 integral of sine to the power of n minus 2x into sine square, which will give you sine to the power of n x dx, and therefore I replace that as in. Now you club this in on the other side and bring it that side. So taking in as common, 1 for this in and plus n minus 1 from this in, so that 1 and 1 reduces to give you n in is equal to minus sine to the power of n minus 1x cos x plus n minus 1 into I n minus 2. Now you divide throughout by n, and so that gives you a reduction formula in as minus 1 by n sine to the power of n minus 1x into cos x plus n minus 1 by n into I n minus 2. Now this formula you can just keep repeating. Now for I n minus 2, if you want to replace, you put here n minus 2, then this n will be n minus 2, and here it will be n minus 2 minus 1, and here it will be in the numerator n minus 2 minus 1 divided by n minus 2. So that will give you in terms of n minus 3 by n minus 2, and you can proceed till you end up with an I0 or I1. So if n is an even number, you will end up with I0, and I0 by definition is going to be integral of sine to the power of 0 x dx, which is just 1. So integrating, you get a value x. And if it's an odd number, you will end up with I1. So if n is an odd, I am ending up with I1, and I1 by definition is going to be integral sine x dx. On integrating, you get minus cos x. So this is how you will end up if there is no limits. And normally we have this integration with the limits varying from 0 to pi by 2. So when you have 0 to pi by 2, where I have this formula in is equal to, I'm going to substitute here. So when you substitute limits here as 0 to pi by 2, now upper limit is pi by 2, sine pi by 2 will give you 1, but cos pi by 2 is 0, so the value of the upper limit is 0. And when you take the lower limit, sine 0 is 0 and cos 0 is 1, so the lower limit is also 0, and therefore this term will vanish. So now in will reduce to n minus 1 by n into in minus 2 and so on. So you will have this formula after substituting the limits as in is equal to n minus 1 by n into in minus 2. Now replacing in minus 2 as n minus 3 by n minus 2 into I n minus 4. You can proceed like that till you end up with n is odd or n is even. And so when it is I naught, when it is I naught, it was x limits varying from 0 to pi by 2. So upper limit is pi by 2 minus lower limit is 0. So it will end with a pi by 2 when n is even. So in will be n minus 1 by n into n minus 3 by n minus 2, etc., up into half into pi by 2 if n is even. And similarly, if you had an odd value, then you ended up with I1, the value was minus cos x, limits varying from 0 to pi by 2. So upper limit will be cos pi by 2, which is 0. Lower limit is cos 0 is 1. For lower limit, there's a negative sign making it as positive. So you get a value 1 here. And so when it is odd, it will end with a 2 by 3. So thus you have in is equal to n minus 1 by n into n minus 3 by n minus 2, etc., into 2 by 3 if n is odd, and it will be half into pi by 2 if n is even. And this formula I have used in one of the definite integral problems. Same way, when you want to do it for cos, in is equal to integral cos to the power of nx dx, where n is in positive integer. I'm going to make a substitution. U is equal to cos n power n minus 1x. So du is n minus 1 into cos to the power of n minus 2x into differential of cos x is minus sin x. And dv is cos x dx, and integrating you get v is equal to sin x. As usual, you have it as in is equal to integral of cos to the power of n minus 1x into cos x dx, which on integrating by parts you get uv minus integral v du. I'm just substituting, so you get cos to the power of n minus 1x sin x minus integral of sin x into n minus 1 into cos to the power of n minus 2x into minus sin x dx. As usual, this I get sin x into sin x, sin square x, which is replaced by 1 minus cos square x. Then 1 into cos to the power of n minus 2 will become 1 integral, and cos square into cos to the power of n minus 2, reducing it to cos to the power of nx, will become the second integral. And in the same format, in will now reduce to cos to the power of n minus 1x sin x plus n minus 1 into in minus 2 minus n minus 1 into in. Bringing the in on the other side and simplifying, you get in is equal to your formula here as cos to the power of n minus 1x sin x divided by n plus n minus 1 by n into in minus 2. Proceeding as before, when you substitute your limits 0 to pi by 2, and you get the same value as before, the same formula that we had for sine, you will get the same formula. Another reason for that is you can use your definite integral properties here to prove it, because integral 0 to pi by 2 sine to the power of nx dx can be rewritten as sine to the integral 0 to pi by 2 sine to the power of n into pi by 2 minus x dx. Sin 90 minus theta is cos theta, so that reduces to integral 0 to pi by 2 cos to the power of nx dx. So I naught I1 are the same for both integral 0 to pi by 2 sin power nx dx and integral 0 to pi by 2 cos to the power of nx dx. In general, for both of them, you have the general formula as in is equal to n minus 1 by n into n minus 3 by n minus 2, etc., up to 2 by 3 if n is odd, and if it is n minus 1 by n into n minus 3 by n minus 2 into half into pi by 2 if n is even, when there is a limit 0 to pi by 2. For today, let's remember these formulas, and you will have to remember it because we might use it in various chapters whenever we are doing the integration, because every time you get integral of sine to the power of 5x or sine to the power of 8x, etc., I am not going to do the integration. I will directly use this reduction formula. Thank you. Meet you in the next episode.